Hello everyone, welcome to Math Archives. In this video, let me discuss about Fourier series in detail. So you know already Fourier series is invented by French mathematician Fourier. He introduced this series in 1822 while he was investigating the problem of heat conduction. So in general, we say Fourier series is a series of sines and cosines. Okay. So before that, you should know what is a periodic motion. Motion repeated in equal interval of time. If it is like that, means we have to say that is in periodic. So based on that, we have to define periodic function. A function f of x is to be periodic if and only if f of x plus p is equal to f of x is true for some value of p and every value of x. So these are all the things that we have discussed already in detail. So for more details, you refer the video. I will give the link of that video in the description box. Okay. Let me now move on to Deterrent condition. So any function f of x can be developed as a Fourier series. F of x is equal to a0 divided by 2 plus sigma n varies from 1 to infinity a n cos n x plus sigma n varies from 1 to infinity b n sin n x. So where a0, a n and b n are constants, provided it satisfies the following three conditions, which is known as Deterrent condition. So this gives you the existence of Fourier series. But the first condition is f of x is periodic, single valued and also finite. The second one is f of x has a finite number of finite discontinuities in any one period and no infinite discontinuity. That's why we have only sine and cosine terms in Fourier expansion. Okay. So f of x has at the most a finite number of maxima and minima. Okay. Next one, Fourier series. So let me now enter into the concept of Fourier series. So any function f of x as a periodic function and satisfies the Deterrent condition means then you can express the function as an infinite series of the form f of x equal to a0 by 2 plus sigma n varies from 1 to infinity a n cos n x plus sigma n varies from 1 to infinity b n sin n x. Here a0, a n and b n are constants. Here I have to say one more thing. Here the Fourier coefficients a0, a n and b n are calculated by make use of the Euler's formula. Now we now move on to what is Euler's formula. So if any function f of x is defined in interval c to c plus 2 pi, here x takes a value from c to c plus 2 pi and can be expanded in an infinite trigonometric series of this form. Here a0 is calculated by make use of the formula 1 over pi integral c to c plus 2 pi f of x dx, and an is calculated by make use of the formula 1 over pi integral c to c plus 2 pi f of x cos n x dx, and bn is calculated by make use of the formula 1 over pi integral c to c plus 2 pi f of x sin n x dx. Here c takes two possible set of values. Either c takes the value 0 or c takes the value minus pi. If c takes the value 0, what happens? Are the limits changed from c to c plus 2 pi to 0 to 2 pi. So this is one set of series we have to discuss. Okay, this is of range 0 to 2 pi. Suppose if c takes the value minus pi, what happens? Our interval becomes minus pi to plus pi, isn't it? C to c plus 2 pi, that is minus pi, one of the pi being cancelled, so minus pi to pi. So we are under Fourier series. So we have two categories. Okay. So either the interval is from 0 to 2 pi or minus pi to pi in pi form. Like that we have to change this to L form. So instead of c to c plus 2 pi, if it takes L plus 2 pi. So this is under L form. Okay. That is what we are going to discuss in the next video. So let me explain this clearly to you now. So Fourier series can be generally of two kinds we are going to discuss. One is under pi form, another one is under L form. So in pi form only, in this video, throughout this video we have to discuss A to Z about pi form only. In my next video we have to discuss about L form. Okay. So in pi form we have two categories. Either it is of full range or half range. If it is of full range means either the series is, the function is in the defined in the interval 0 to pi or minus pi to pi. So if any function is defined under 0 to 2 pi and minus pi to pi, that is under the category of full range. If any function can be defined in an off range, that is 0 to pi, then we have two categories. Either we can form sine series or cosine series. Okay. So these are all the things we are going to discuss in this video. Okay. Now let me now move on to Fourier series under 0 to 2 pi. So if any function is defined in an interval 0 to 2 pi and also periodic, satisfies a Deterrent condition, then f of x can be expressed in this form, where a0 is calculated by make use of the formula a0 is equal to 1 over pi times 0 to 2 pi f of x dx, and an is calculated by making use of the formula 1 over pi into 0 to 2 pi f of x cos nx dx, and bn is calculated by making use of the formula 1 over pi into 0 to 2 pi f of x sin nx dx. Here the values are all called Fourier coefficients. Okay. Now your question is, so if it is under 0 to 2 pi, okay. So we have a general form. For that we calculate the values of a0, an and bn by make use of the Euler's formula. Suppose if it is under minus pi to pi, then immediately our answer is the same as that of 0 to 2 pi, isn't it? Yeah, but that is not the case. Okay, so if it is under minus pi to pi, this is also one of the case, that this is not the whole thing we have to discuss under minus pi to pi. Let me explain clearly to you now. If it is under 0 to 2 pi means we have only one series. The general form is of the form f of x equal to a0 by 2 plus sigma n varies from 1 to infinity an cos nx plus sigma n varies from 1 to infinity bn sin nx. We have a unique general form of f of x for which we calculate a0, an and bn. But if it is under minus pi to pi, we have three categories. Either the given function is of even or odd if it is neither even nor odd. So under minus pi to pi, we have the case of odd and even functions. Okay, so the case of odd and even functions arise only for intervals of type minus pi to pi. So for that, let me explain what is the meaning of odd and even function to you now. Even and odd function cases arise only functions is defined under minus L12 or minus pi to pi. In this video, we have to discuss only pi form. So I will explain what is the formula we are going to use and how to deal with the problems under minus pi to pi in detail. Okay, functions defined in a range like 0 to 2 pi and 0 to 2l, the case of odd and even doesn't arise. Okay, only for the intervals of type minus pi to pi alone. So any function f of x is said to be an even function if f of minus x is equal to f of x, then function is an even function. For example, we have to give so many examples: cos x, x square, absolute x, x sin x. These are all even functions. If you replace x by minus x, what happened? Cos of minus x is nothing but cos x itself, because you know cos of minus theta, cos theta. So when you replace x by minus x in a given function, you get the same function, means that is an even function. Any function f of x is said to be an odd function if f of minus x gives you minus of f of x. For example, here itself we can give so many examples like x, x cube, sin x, x cos x. These are all examples of odd function. That is, if you replace x by minus x, what happened? Suppose if you take x, f of x as x cube, replace x by minus x, what happened? Minus x the whole cube, right? Minus x the whole cube is nothing but minus of x cube. That is, minus of x cube is nothing but your given function. So if it is like that, then given function is of odd type. So here you have to remember some of the points. That is, the integral from minus a to a f of x dx can be written as 2 times integral from 0 to a. Okay, twice 0 to a, function is of even type. If it is 0, means that is of odd. And when you multiply even function and even function, you get an even function. You multiply odd and even and odd gives you an odd function, and odd function gives you an even function. So now let me show you the table for your reference. Now you got a clear idea about the formulas that we are going to use under minus pi to pi. Okay, so in 0 to 2 pi we have only one general form of f of x, whereas in minus pi to pi we have three distinct forms. That is, if it is even, odd and neither even nor odd. If it is even means we can have the values of only a0 and an, the value of bn becomes 0. So your f of x is of the form a0 divided by 2 plus sigma n varies from 1 to infinity an cos nx alone. This is the general form under even. If it is of odd, the a0 an becomes 0, the values become 0, we have only bn alone. So in that case, your general form is of the form that series consists of only bn, sin nx alone. If it is neither even nor odd, means you can calculate the values of a0, an and bn, and the general series is same as that of the series in 0 to 2 pi. a0 by 2 plus sigma n varies from 1 to infinity an cos nx plus sigma n varies from 1 to infinity bn sin nx. So these in such cases, these two of them having the same series, but the formula seems to be different. Okay, so here the limit is from 0 to 2 pi, but here the limit is from minus pi to pi. Okay, only the general form of f of x alone. Okay, now let me now move on to again the categories of Fourier series. So in pi form, as I told you already, we have two cases, that is full range or half range in 0 to 2 pi and minus pi to pi. If it is 0 to 2 pi, we have a unique form. So for that we have separate formulas for calculating the values. But whereas in minus pi to pi we have three categories. If it is even, if it is odd, if it is even or odd. So in such cases we have three different cases. So for that we have to deal with the concept of odd and even functions. Next we move on to half range. If it is, so instead of defining the function is a full range like 0 to 2 pi or minus pi to pi, sometimes the functions can be defined in a range like 0 to pi. So in such cases we can extend this function either in terms of sine series or cosine series based on our convenience. Okay. So now let me move on to the concept of half range series. So the property of extending a function defined in an interval 0 to pi, we have to give two distinct half range series, that is in terms of sine series or cosine series. So if it is in half range series, as I told already, we have two categories. So under pi form and also for L form. We have to deal only with pi form. So in pi form, if it is cosine series means that consists of only a naught an, the value of bn becomes 0. If it is sine series means a naught an becomes 0, we have only bn alone. So f of x seems to be like this. Look at here, these formulas coincide with the formula under even and odd. This is similar to the same formulas under minus pi to pi. Okay, the functions defined under minus pi to pi. If it is even, we have the same case. If it is odd, this is same case. So no need to remember this formula as a different formula. Okay. Next, we move on to complex form of Fourier series. We can express the given functions in an exponential form. That is, if it is in, suppose if you want to give the complex form of Fourier series, we have to look at what is the given interval. If it is from minus pi to pi or 0 to 2 pi or 0 to pi 2. So here itself we have to deal only with pi form. So in pi form we have these three cases, isn't it? If it is minus pi to pi, this is the general Fourier complex form. This gives you the complex form of Fourier series in general. If it is 0 to 2 pi, this is f of x, and 0 to pi. So for which, if it is f of x means you calculate value of Cn by make use of this formula. If it is from 0 to 2 pi, you make use of this formula for calculating Cn. If it is from 0 to pi, you make use of this formula for calculating the value of Cn, and substituting in f of x gives you the complex form of Fourier series. Okay. Next we move on to Rms value. One of the important thing you have to remember. So if it is under minus pi to pi, 0 to 2 pi and 0 to pi, your Rms value can be calculated by make use of the formula y bar square is equal to 1. That is nothing but 1 by b minus a. B minus a is nothing, 1 by b minus a. B is nothing but interval is type a comma b means b minus a means pi minus of pi, that is 2 pi. Integral from a to b f of x whole square. A to b is nothing but minus pi to pi. Isn't this? A to b f of x whole square dx. Okay. So this is the general form. So for that interval minus pi to pi, we have this y bar square, and 0 to 2 pi and 0 to pi we have y bar square like this. Oh, in 0 to pi, look at here, we are 2 times 0 to pi. Okay. Next, Parseval identity, one of the important thing. So you should remember. So if it is of interval 0 to pi, if the Fourier series of this form like this, so in such cases we make use of the Parseval identity. That is, for deduction part we make use of Parseval identity. Okay. So this is the Rms value that is on left hand side, that is equal to a naught square by 4 plus 1 by 2 sigma n minus 1 to infinity a n square plus b n square. Like that for minus pi to pi, 0 to pi. If it is in cosine series means we make use of this one. If it is, this is for cosine series. That's why it consists of only a naught a n. If it is in terms of sine series means they consist of only sine term alone. Okay. So Rms value to the left hand side, that is equal to 1 over 2 sigma n minus 1 to infinity b n square. So these are all the list of formulas we have make use of for deduction part. Okay. Next, one of the important thing you have to remember, some of the important formulas here I am going to list out for your reference. So first important thing is you should know integral UVDS, that is whenever the product of functions is inside the integration means you don't know how to evaluate this integral and getting the value. So for that we make use of this Bernoulli's formula to evaluate the integral. That is integral u v dx equal to uv1 minus u dash v2 plus u double dash v3 x minus etc. Here both u and v are functions of x. That is u dash is nothing but once you have to differentiate u with respect to x. U double dash means you have to differentiate u 2 times with respect to x etc. like that. So u dash, u double dash, u triple dash are successive derivatives of u, whereas v1 is nothing but you have to integrate v. What is your v here? V alone. integral v dx. v2 is nothing but you have to integrate 2 times with respect to x. Okay, v. But already we have to integrate v one time. So instead of doing like that, so you have to integrate v1 once again with respect to x. That gives you your v2. So v1, v2, v2, v3, etc. successive integrals of v, like that. So for your reference, I have to write down v3 too. v3 is nothing but you have to integrate v3 times. So instead of doing like that, you have v2. So you have to integrate once again with respect to x, means that gives you v3, like that. Sin 2 is so here I have to list out some of the trigonometric formulas. Sin 2a is equal to 2 sin a cos a, whereas cos of minus theta is equal to cos theta, whereas sin of minus theta is equal to minus sin theta. So cosine is an even function, sine is an odd function. Sin squared is equal to 1 minus cos 2a divided by 2, and cos squared is equal to 1 plus cos 2a over 2. And the next, these are all some basic formulas you know already. Integral x bar n dx is equal to x bar n plus 1 divided by n plus 1, whereas d by dx of x bar n is equal to n x bar n minus 1. Integral sin x dx is nothing but minus of cos x, whereas integral cos x dx is nothing but plus sin x. Okay, and integral sin 2x is nothing but dx is equal to minus cos 2x divided by 2, and integral cos 2x dx is equal to sin 2x divided by 2. And integral sin n x dx is equal to in general minus cos n x divided by n, whereas integral cos n x dx is equal to sin n x divided by n. So these are all the values you should remember while substituting the limits. Cosine 0 takes the value 1, cos 2 pi is plus 1, cos n pi is minus 1 whole power n, cos 2 n pi plus 1, whereas cos pi value minus 1, cos pi by 2 0. Whereas in case of sine terms, sine value sin 0 0, sin 2 pi 0, sin n pi equal to 0 if n is an integer. Okay, this is very important thing. So here we have to mostly dealt with only integer case, so that's why I am not mentioning here. Sin 2n pi is also 0 when n takes integer value, sin pi 0, whereas sin pi by 2 takes the value 1. Now, these are all the important things you should remember. Okay, these are all the formulas you should remember. For that, we make use of these formulas. So whenever the product of functions and trigonometric functions means to evaluate that integral, we have to use this equalities to convert into and to integrate or differentiate the given functions. Okay, to simplify our calculations, we make use of these type of trigonometric equalities. Okay, sin of a plus b is equal to sin a cos b plus cos a sin b, whereas sin a minus b is equal to same thing. Here you have minus, where cos a plus b is equal to cos a cos b minus sin a sin b, whereas cos a minus b equal to same thing. Here you have plus. So if you add these two, what you get? 2 times sin a cos b is equal to, and if you have to subtract these two, you have 2 cos a sin b. Okay, suppose you have to add this one plus this one. Okay, you have 2 cos a cos b, that is cos a plus b plus cos a minus b. Suppose you had to subtract what you had from this one, minus, that is cos a minus b minus cos a plus b is equal to 2 sin a sin b. Next important formulas, these are all the things that you have derived from these formulas. If you know sin a plus b, sin a minus b, cos a plus b, if you know these formulas, from this you can derive this. First one I have to evaluate for your reference. This is of the form cos n plus 1 2 pi. This is of the form cos, if you take 2 pi inside, what happened? Cos of 2n pi plus 1. That is, you know, cos a plus b is nothing but cos a cos b cos 2n pi plus cos 2 pi, isn't it? Cos a plus 2n pi plus cos 2n pi plus 2 pi is equal to cos a cos b minus sin 2n pi sin 2 pi. You know all these values. Cos 2n pi 1, cos 2 pi value 1, and sin 2n pi sin 2 pi value becomes 0. So I am substituting here and getting the value. So no need to remember all these values. Okay. So if you know the basic formulas of this trigonometric, so from that you can find the values of either cos n plus 1 2 pi or n plus 1 by 2 2 pi or cos n plus 1 pi, likewise in terms of sin 2. Okay. Now, in finding the denominators of a n, that is Euler constants, so for to give the general form of Fourier series, you have to calculate the values of a naught, a n and b n. Okay. So for calculating these values, look at the denominator. So if it is a naught, no need to worry about a naught, that is a constant term. So coming to the case of a n and b n, So if the denominator consists of n square minus 1 means you have to go for the particular case and calculate the values of a1, b1. So this holds only for the functions involving sin x, cos x. That is, if any given function involving trigonometric functions, then only we have these cases. Okay, suppose a given function involving only algebraic terms like this, we no need to worry about these cases. Okay, so these cases arise only for the function involving the trigonometric functions. Okay, so if it is so, we have to go for the particular case and calculate the values of a1 and b1. Next we move on to the convergence of Fourier series. If the given, that is, a point is a continuous point, means we have to substitute the value directly and to get the value of the function at that point. If it is discontinuous points, means we have to discuss two cases, whether where the discontinuity, first one we have to find out whether the discontinuity arises at the end point or at the middle point. If it arises at the end point, means we have to take the average of the extremities at the end point. If it is at middle point, means we have to take the average of left hand limit plus right hand limit divided by 2. Okay. So next, for changing the summation is from r to infinity to sigma 1 to infinity, you have to replace the value inside the summation. Okay, the value n by here 2n minus 1 means then the summation change from r to infinity to 1 to infinity. Suppose if you replace the summation from even to infinity to 1 to infinity means you have to replace inside the summation n value by 2n. By doing so, the summation of the values of n takes in the value from 1 to infinity is converted by replacing n by 2n. Next, problems on Fourier series. Now we enter into the important category. Listen carefully. So we have discussed all of the basic things involved under Fourier series under 0, 2 pi and minus pi to pi, and also the half range series. Now let me take sample problems. Here I have to take two problems under two different intervals. I have to take the same function f of x equal to x square here itself. But the functions are defined here minus pi to pi and here 0 to 2 pi. And also we have to work on the deduction part too. So first I have to take this problem, that is f of x equal to x square, and let me find out the general Fourier series representation along with let me deduce the series that is given in the problem. Okay. Now, so expand f of x equal to x square as a Fourier series in an interval 0 to 2 pi, and we have to deduce this series. So first what we have to do, first we have to write out the given function along with the interval. Interval is very much, if it is 0 to 2 pi no need, you have to carry on as it is. If it is under minus pi to pi, then only we have to discuss about whether the given function is of even or odd, something like that. Okay. So the given function is under the interval 0 to 2 pi, no worry. So write out the general form for which you have the formula for calculating the values of a0, an and bn. So for make use of this formula, first we calculate the value of a0. So 1 by pi integral 0 to pi f of x dx, where f of x is x square. So integrating x square, what you get? X cube divided by 3. So first we have to substitute the upper limit. So replace x by 2 pi. And next you replace x by 0. 0 means this term becomes 0. So 2 pi the whole cube, simplifying this you get 8 pi square divided by 3. Next we calculate the value of an. For that we make use of the formula an is equal to 1 over pi integral 0 to 2 pi f of x cos and x dx, where f of x is x square. Just in your next step replace f of x by x square. This is how the form product of functions. So integral u v dx. So for that we make use of our formula integral u v dx equal to u v1 minus u dash v2 plus u double dash v3. U is x square, u dash is differentiating this 2x, u double dash 2. Suppose if you are going to differentiate once again means u triple dash becomes 0. That's why I have to stop up to u dash double dash. Here v is cos n x and v1 is cos n x. Integrating cos n x you get plus sin n x divided by n. v2 is nothing but integrating sin n x, you get what you get, minus cos n x divided by n. Already you have n in the denominator, that's why here you have n square. And v3 is nothing but minus 1 by n squared is constant, isn't it? So you have only cos n x. Integrating cos n x, you have sin n x divided by n. Already you have minus 1 divided by n square, so that's why you have minus by n cube. So this is how the form integral u, this is your v, substituting in the formula u v1 minus this is your u dash v2 plus u double dash v3. Substituting the formula and applying the limit from 0 to 2 pi. So now what I am going to do in the next stepping, just simplifying the symbols. So now I have to make this minus and minus as plus here and plus minus as minus here. That's what only I have to do in the next step. No more simplification in the next step. In your next step, what you are going to do is, I am going to substitute the limits. So mark the x terms. These are all the places we have x. Suppose if you substitute x is equal to 2 pi first, okay, x is equal to 2 pi, what happens? If you substitute x is equal to 2 pi sine 2 pi, this term becomes 0 and this term becomes 0. Okay, you have only the second term alone, because 2 times 2 pi cos 2n pi value plus 1. So that's why you have the second term alone. 2 times 2 pi cos 2n pi values plus 1 over n square minus, coming to the lower limit. So if you replace 0, 0, this term 0 and x, because sin 0 value 0 and also this x square means 0 square 0. Second term, if you replace x by 0, this term 0, sin 0 value 0. So you don't have any other terms. So simplifying this, you get the value of a n as 4 divided by n square. Next we calculate the value of bn. So 1 over pi integral 0 to pi f of x sin n x dx. So replace f of x by x square. This is a product of function. This is of the form integral uv dx. This is it. So you know the formula. Integral uv dx equal to uv1 minus u dash v2 plus u double dash v3. So the same thing we did already. Now we have v is nothing but sin n x. So your v1 is minus cos n x by n. v2 is minus sin n x by n. v3 is cos n x divided by n cube. So substituting the formula u v1 minus u dash v2 plus u double dash v3. In your next step, what I am going to do, just simplifying the simple. So these are all the problems. Listen carefully. These are the problem we have discussed already. I am just give you the link in the description box. Okay, that's why I am just go fast. And 1 over pi, I am just simplifying the symbols. Now what I am going to do, I just replace the values of x by 2 pi first. If you replace x by 2 pi x square, that is 2 pi square cos 2n pi. You know the value of cos 2n pi. The value of cos 2n pi is plus 1. Next, coming to the second term, sin 2n pi. You know the value of sin 2n pi. Sin 2n pi value is 0. Coming to the third term, 2 times cos 2n pi. Cos 2n pi is 1. So upper limit over. Minus, coming to the lower limit. If replace x by 0, what happens? X by 0 means 0 into anything 0. First term 0. Coming to the second term, x, here product, x in product. So you replace x by 0 means you get 0. Coming to the third term, cos 0 value 1. Isn't it? Cos 0 value 1. So you have 2 times divided by n cube. So simplifying this, you get the value of bn as minus 4 pi divided by n. So we get the values of a0, an and bn. Substituting in f of x gives you the general Fourier series representation of the given function. So from which we get, this is the Fourier series representation of the given function f of x. So your f of x is nothing but x square, that is defined in interval 0 to pi. So this is the general form of the Fourier series for the given function f of x equal to x square, defined in an interval 0 to 2 pi. Now let me now move into the deduction part. So in this part we have to deduce the series sigma n varies from 1 to infinity 1 over n square is equal to pi square by 6. This is what we are going to deduce. Look at this general form we have just now derived for the given function f of x equal to x square. So in the deduction part, the series is having the denominator n square. So we have to deduce the cosine series. As I told you already, most of the cases cosine series is obtained by putting either 0 or pi. If you substitute 0 means you get series of all positive terms. If you substitute x equal to pi means you can get series of alternatively positive negative. This is cos n pi is equal to minus 1. That's why we have to get series of alternative terms. So here I have to sum up the series of all positive terms. This is what I am going to deduce. So for that I have to choose x equal to 0. Okay, so put x equal to 0, which is, so if it x equal to So if it is x equal to 0 means definitely you can first find out whether the point is continuous point or discontinuous point. Here 0 is a discontinuous point which occurs at the end point of the interval, isn't it? As I told you already, if the point is belonging to the interval means that is a continuous point. If it doesn't belong to the interval means that is a discontinuous point. So here 0 the point is not included. Okay, so this is a point at discontinuity at the end point. So end point of the interval means f of x equal to 0. Just replace x by 0 here and here and here. So if you replace cos 0 value 1 whereas sin 0 value 0, so we don't have this term. If you substitute x equal to 0 and let me show you the convergence of Fourier series table once again for your reference. If the discontinuity arises at the end point means we have to take the average of the values at the endpoints, right? Now, so for that you have to take the interval is from 0 to 2 pi, so f of 0, f of 2 pi, average of the extremities, so 0 to 2 pi. So you have to calculate the values of the functions at f of 0 and f of 2 pi, and you have to add and divide by 2. That is equal to, so we have the same right hand side, the function value f of 0. So you know f of x is nothing but the given function, f of x is x square, isn't it? So 0 square plus 2 pi the whole square, f of 0 is 0 square and f of 2 pi is nothing but, replace x by 2 pi, you had 4 pi square over 2. Simplifying this, okay, so you get sigma n varies from 1 to infinity, 1 over n square is equal to pi square by 6. Expanding this, you get 1 by 1 square plus 1 by 2 square plus 1 by 3 square, that is equal to etc., that is equal to pi by 6. So by substituting x equal to 0 for cosine series, we get series of all positive terms. Okay, that's all. The deduction part is over. So let me now move on to the second problem. So here itself I am going to take the same problem, but the function is defined at an interval minus pi to pi. Okay, that is the only difference. Okay, now write down the given function along with the interval. F of x equal to x square, that is defined at an interval minus pi to pi. As I told you already, you have to write out the function along with the interval, that is very missed. So if the function is defined as an interval minus pi to pi means we have three cases. Either it is even or odd, or neither even nor odd. The case of even and odd function arise only for the interval of type minus pi to pi or minus L to L. But in the case of odd and even doesn't hold for the intervals of type 0 to 2 pi and 0 to 2L. So interval is very must for determining general Fourier series for the given function. Okay, so here the function is defined at interval minus pi to pi, so immediately we can verify whether the given function is of even or odd. For that you have to replace x by minus x in the given function. If you replace x by minus x, what you get the same function, which means the function is even. If it is even function means immediately you can write the value of bn is equal to 0. Let me show you the formula table for your reference. So we have three categories. So now we are under this category even. If it is even means we have to calculate only a not an. So no need to calculate the value of bn. We can directly write value of bn as 0. So this is your general Fourier series f of x. So we make use of these two formulas for calculating a naught and an. So first we have to calculate the value of a naught. For that we make use of this formula. Replace f of x by x square, and integrating and substituting the limits you get the value of a naught. This one. And next you calculate the value of an. So for that we make use of this formula and replace f of x by x square. This is of the form integral uv dx. So for that we make use of the Bernoulli's formula, uv1, that is integral uv1 minus u dash v2 plus u double dash v3. So in the next step what I am going to do is I am just simplifying the symbols alone. So now simplifying the symbols, after that you have to mark the expositions. Now let me substitute the limits. Upper limit minus lower limit. If you substitute the upper limit, what happens? So sin n pi, you know the value of sin n pi. Sin n pi value 0, whereas cos n pi value minus 1 whole power n. So sin n pi 0 means first term 0 plus coming to the second 2 pi cos n pi value minus 1 whole power n over n square. Coming to the third term sin n pi 0, upper limit over minus. Coming to the lower limit 0. So x is in product, first term 0, here second term also x is in product, so second term 0, coming to the third term sin 0 values you know already, that is 0. Simplifying this you get the value of an. And substituting in f of x gives you the general form of f of x. Okay, that is the Fourier series representation of the given function f of x is equal to x square, that is defined at an interval minus pi to pi. Now, so after getting the series, now let me now enter into the problem. So function is defined in closed interval minus pi to pi. So listen, f of x equal to pi square over 3 plus 4 times sigma n varies from 1 to infinity minus 1 whole power n over n square cos n x. From this I am going to deduce these three series. So for that, first I am going to give you a short intro about convergence of Fourier series. If it is continuous points means you have to substitute the value directly. If it is at end point, you have to take the average of the values at extremities. If it is middle point means you have to take the average of left hand limit plus right hand limit divided by 2. Now let me now move on to the deduction part. Now listen carefully. So we have cosine series alone. In the cosine series we have the denominator n square. As I told you already, in most of the cases cosine series is obtained by substituting either x equal to 0 or x equal to pi. X equal to 0 gives you series of all positive terms. X equal to pi gives you series of all alternatively positive negative. But look at here, already we have minus 1 whole power n. If you substitute x equal to 0, what you get? X in this problem, if you substitute x equal to 0 gives you alternatively positive negative, since we have already minus 1 whole power n in the series. Okay, here x equal to pi gives you series of all positive terms, because already you have minus 1 whole power n. You substitute cos n pi is equal to minus 1 whole power n, means what happens? Minus 1 whole power 2n, that becomes 1. So if in this problem alone x equal to 0 gives you alternatively positive negative series, and x equal to pi gives you series of all positive terms, since we have minus 1 whole power n. Next, now let me substitute x equal to pi, which is a continuous point, because the function is defined at interval minus pi to pi, the closed interval. So x equal to pi gives you, that is a continuous point. If it is continuous point, we have to directly substitute, that is your f of x is nothing but x square. Just replace x by pi as usual. That is continuous means replace x by pi means pi square. So here you have x equal to pi means you have cos n x minus 1 whole power n. So here minus 1 whole power 2n. Minus 1 whole power 2n is plus 1, that's 1. Here minus 1 whole power n minus 1 whole power n becomes 1. That's all. So keeping this summation one side, take the remaining terms to other side, you get or sigma 1 by n square is equal to pi square by 6. Expanding this, you get 1 by 1 square plus 1 by 2 square plus 1 by 3 square, that is equal to pi square by 6. Next we move on to the second deduction part. Now we substitute x equal to 0. Here the function is defined at interval minus pi to pi. So if it is 0 means point is approximately here. That is a continuous point. So if it is continuous point, mean f of x equal to x square is a point. So we have to directly replace. So cos 0 value 1. So simplifying and take this series along this side, take the remaining terms to the other side, you get this series. And now let me now move on to the third deduction part. This is obtained by adding the first and second, gives you the third. Excuse me. Now already we have discussed these problems, okay, in detail. So the link is given in the description box. For more details you refer the link. Okay, now let me now move on to Fourier series. I have to take the same function f of x equal to x and find out the Fourier cosine and also sine series for the same function f of x equal to x. So let me show you the formula table for your reference. Now let me now move on to the problem. Obtain the Fourier cosine series for f of x equal to x, define interval 0 to pi. So if it is cosine series means that consists of only a naught an. So now let me first calculate the value of a naught. For that, integrate x, you get x square, and simplifying this you get the value of a naught. And we calculate the value of an. For that, make use of this formula, replace x by f of x by x. This is of the form integral uv dx. So substituting formula uv1 minus u dash v2, that's alone. So substituting the limits and simplifying, you get the value of an. So if it is like this, you can now convert this in terms of odd and even. For that you have to replace this power of n by odd terms. If it is replaced by odd value, what you get? Minus 2, that is minus 4 times n by n square by n. If it is even, that is minus 1 whole square minus 1, that is 1 minus 1, 0. So if it is even means we don't have the value of an. If it is odd values alone, the value of an exists. That is the meaning of that. So substituting in the f of x gives you the value of, that is the general form of Fourier series of the function f of x equal to x, that is defined in interval 0, 5. So this is the offerings Fourier cosine series for the function f of x equal to x. Next we find out the Fourier sine series for the same function f of x equal to x. So if it is sine series means consists of only sine terms. So for that we make use of this formula for calculating bn. So this is a formula for calculating Bn. Just replace f of x by x sin x. This is of the form u v dx. So u v1 minus u dash v2. This, okay. Now simplifying this, you get the value of Bn is equal to minus 2 times minus 1 whole power n divided by n. That's all. Substituting here, you get the Fourier sine series, that is half range Fourier sine series, from which we have to deduce the series, isn't it? So for that, let me show you the convergence of Fourier series. If it is continuous points, means what you do? Substitute the value directly. So now we have to take x equal to pi by 2. So because the function is defined interval 0 to pi, pi by 2 is the center point. So that is a continuous point. So f of x at pi by 2 is nothing but that is equal to 2 times. The expansion is here. So sin pi by 2 values. Okay, here I have to say one more thing. Sin pi by 2 value 1. This is sin pi. Sin pi value 0. Sin 3 pi by 2 value, that is minus 1. Sin 4 pi by 2 is nothing but 0. Sin pi by 2 is nothing but plus 1. Okay, that's all. Simplifying this, you get the series. Now find the complex form. Here f of x is nothing but given as e power x, that is under minus pi to pi. Now if it is under minus pi to pi, means this is a general form for which we make use of the value of Cn. You calculate the value of Cn. Okay. So now given f of x, this is a general form to find the general form, we make use of this formula. So Cn is equal to, this is a formula, you replace f of x by e power x. Your e power x, here x is a constant term, so take it common, and integrating you get e power x divided by the coefficient of x in the denominator. Next, upper limit minus lower limit, let me substitute. So then next term, you have to take these two terms common and take it outside, and you have to take this pi inside. Okay, that's all. So e power pi, you take it as it is, e power minus I theta. You know already, cos theta minus I sin theta. So instead of theta, here you have n pi. Likewise, here itself you have to expand e power I n pi as cos n pi plus I n sin n pi. You know the value of sin n pi. Sin n pi 0. And value of cos n pi is minus 1 whole power n. Okay, that's all. So here you have minus 1 whole power n is a common term, take it outside. So you know e power x minus e power minus x divided by 2 is equal to sine, hyperbolic sine. Okay, sine h, not sine of hx. This is circular function. Okay, hyperbolic sine of x, that is like that. If you replace this by e power pi minus pi is nothing but 2 sine, hyperbolic sine pi. That's all. This gives you Cn value. Substituting in f of x gives you the complex form of the Fourier series of the given function f of x equal to e power x. Okay, so listen carefully. Here the denominator consists of 1 minus in. So if the denominator is a complex number, so what we do as usual, you have to convert it into a real number. For that you have to multiply both numerator and denominator by the its conjugate. So what is the conjugate of 1 minus in? 1 plus in. You just multiply both sides. Okay, so there is both numerator and denominator, so that the denominator is a real number. So that is the main purpose. For that we have to multiply both numerator and denominator by its conjugate. Okay, sometimes most of them do, you just stop the value of Cn up to this, but that is not appreciated one. Okay, so if the denominator, not only this problem, whatever may be the problem you have to deal with, whenever the denominator is a complex number, means you have to multiply both numerator and denominator by its conjugate to convert the denominator into a real number. Okay, now let me substitute the value of Cn. This gives you the complex form of the Fourier series. Now let me move on to one more problem. Obtain a half range cosine series and sine series. So why we make use of possible identity, I have to explain here. Okay, and we have two more reduction part here. Let me discuss one by one. So already we have discussed the same series under half range Fourier cosine, isn't it? So if first we have to find out the Fourier cosine series. Already just now we have discussed about this. Okay, a naught an. So a naught, and for calculating an, and finally we have this series, right? Now look at here. After finding the f of x, Look at the deduction part here. The deduction part is twice. Here in our general form of f of x, the denominator of cosine consists of n square. Look at the deduction part, the series consists of that is 2 times more than that we have now. So if it is like that, I just expand this series for your reference. 1 square, 3 square, 5 square. But here we have 3 power 4, 5 power 4 in the deduction part. If you are going to reduce the series, that is 2 times more than that of what we have now, right now. Okay, which means we make use of partial identity. Okay, or otherwise we make use of Fourier convergence theorem to find the series that is mentioned in the problem. Okay, if it is, suppose if you want to reduce a series of 1 by 1 square plus 1 by 3 square plus 1 by 5 square, like that, we make use of convergence theorem. Okay, no need to go for partial identity because the deduction part is coincide with the power of n. That is what we are having f of x. Okay, in the general form of f of x, the cosine consists of n square. So deduction part also our same power, means we make use of convergence theorem either by substituting x equal to 0 or pi and to get the series. Okay, that's all. But here, look at here, cosine series having the denominator n square, whereas the deduction part has the power of 2 times more than that. If it is like that, we make use of partial identity. Let me show you the table for your reference. If it is at 0 to pi, the third one. Okay, that's now we have to discuss Fourier cosine series. So we make use of this partial identity. This is a partial identity, we have to make use of it. Okay, so we make use of partial identity. 1 over pi times 0 to pi f of x whole square dx equal to a naught square by 4 plus 1 by 2 sigma n varies from 1 to infinity a n square. You replace f of x by x, here a naught by pi and a n by minus 4 by n square pi square. Simplifying this, you get x square, integrating you get x cube by 3. So here you have square this, that's all. Now your next step, what you get? So after simplification, you keep the summation alone one side, take the remaining terms to other side. Look at here. So that becomes 2 times more than the general form of f of x what we have derived. So using partial identity, we can reduce the series. That is the only difference. Okay, you know. Okay, next problem. Find the sine series for f of x. This is what this case we have to discussed just now. So now only the direction part seems to be different. Okay, nothing will be different here. Only the direction part. For that, I have to take this same problem here itself. So given f of x equal to x and 0 to pi, so we have to sine series, we have to deduce. For finding f of x, we make use of this formula, and for calculating bn, we can make use of this formula. Okay. Now, so this case we have discussed already. So I am just skip all these steps and write down the general form. Okay, your f of x is equal to sigma n varies from 1 to infinity minus 2 times minus 1 whole power n over n sin n x. Look at here. Okay, I got to mention one of the important point to you now. This is what the given problem. Right now we have to discuss this problem. Okay, but this is the problem we have discussed already. For the same function defined in an interval 0 to pi, we have reduced this series. For the same function defined in the interval, now we have to reduce this series. Okay, you should know what is the difference between these two. Here we have sine series. In the sine series, we have denominator n having the power 1. So if you expand the series, what you get? You just leave these minus sign. Okay, you expand this one, what you get? 1 minus. If it is sine, means that is minus 1 by 3 plus 1 by 5. That is, you have all powers of n is of 1. But here, this is what the series we have to reduce now. Okay, this is of 2 times more than the power of n. That is what we have find out just now. If it is so, we make use of partials. Okay, the series that you are going to deduce is 2 times more than that of the series that you have right now in general form. In such situations, you make use of partial identity. Okay, so this is what the case we have to discuss now. This is what the Fourier series general form we have right now, and this is the case we have discussed already for the same function. If it is so, to deduce this series, we make use of convergence theorem. Okay, we make use of convergence theorem to find the direction part. But here we can't use the convergence theorem because here the power is of 1, here the power is of 2 times more than that. In such cases, for the direction part, we make use of Parseval identity. That is the only difference. Okay. So for make use of Parseval identity, the last fourth one. So your f of x is like this, and this gives you the Parseval identity. So we know Parseval identity for Fourier sine series. This is a Parseval's identity. Substituting the value of f of x, here bn value, we have bn value, square this and integrate this x square, and simplifying this, you get this series. Okay, here look at here, 1 by 1 square plus 1 by 2 square plus 1 by 3 square plus etc. That's equal to pi square over 6. That's all. Okay, so if in the direction part, cosine or sine series having the denominator is same as that of the series in the direction part, means you make use of convergence theorem. If it is 2 times more than that of the series, means you make use of Parseval identity. That is what the only difference. Okay. Up to this, hope you got a clear idea about Fourier series under pi form in detail. Thanks for watching. See you all again in my next video.